Okay, so I'm going to try to make a smaller version now that I've shot from the hip to answer this question already. I'll refine my answer a little here. This is section 7.3, number 8. And when the problem starts, you're not supposed to really know that it comes from section 7.3, which is the section where we learned about the student T distribution. So you're supposed to just be reading the problem and thinking, okay, I have a sample of 7 cars. They're testing for nitrogen oxide emissions in grams per mile. I've got the numbers here from the sample. I'm reading. I have the confidence level that I want my interval to be built around. But nowhere in here do I see it stating what the population standard deviation is. And so that's a cue to me, or clue, whichever way you want to look at it, that it's time to use the student T distribution and not the normal standard distribution. And the reason I say that is because we learned in section 7.2 when to use the population standard, when to use the standard normal distribution if we know the population standard deviation. So here's a list of that. Use the normal one. This is section 7.2, but don't think of it by its section number. Think of it by what parameters you have and don't have. Use the normal distribution or the z distribution if sigma is known and or the parent population is normally distributed and n is greater than 30. Okay. I'm through an or in there. That's not where the or is. It's if sigma is known, you're in this category. So then is the parent population normally distributed, or is the sample size that you're taking greater than 30? Now ours isn't greater than 30. Our parent population may be normally distributed, but it doesn't matter anyway because this is not a condition where we know sigma. Okay, if you don't remember sigma, go to your symbols list. That will be approved. And remind yourself, sigma, the lowercase sigma, is the standard deviation of all the values in the population. It's the population standard deviation. Now, do we know S, or can we find S? Sure. In fact, I'll do that in just a moment. That list, that I was looking at right there, it's made into a nice flow chart, and there's an animation in the flow charts for this, so you might want to watch through that. It'll go through the explanation of the flow chart, and then it'll give you several examples, and that's in the well, there's different locations, but it's specifically in the tools for success, and then it's in the multimedia library. So when we flow through this, we say, is sigma known? And that's what I was reading for most. No, it's not. Okay, so then I'm going to either end up with the T distribution, or I'm not going to be able to do it with what methods I have so far. Well, since the parent population isn't necessarily stated as normally distributed, I might have fallen over here, and then since my sample size was 7, which is below 30, I might have said, hey, I can't do this problem, except it expects an answer. So it must have been that the parent population was normally distributed, or rather, it's allowing us to assume that. Last thing, sorry, let me do one more jump for you. That flow chart is not stated as a flow chart, it's stated as a table, or a list, I'm sorry, bullet points. This also is one of your approved, this is the stats review page in the approved notes. It says it there. I won't read through it, but you can pause or just get it out for yourself and read through it. And it says it on the formula sheet, like the 5th page down. It says it down here. So it's all the same argument. You need to know what distribution you're going to use, and we're going to use T. Okay. Yeah, we're not going to need all this. Let me scoot over. So I'm actually going to take this stats on this. I'm going to run all the summary statistics here. Stick it right there in the table. Okay, max, min, and all that stuff. What I really care about is what's the mean and what's the standard deviation. And the reason why I care about the mean is because that would be the center of my constructed interval, and the interval is a net that I throw out at the true population parameter, the true population mean, and I see if with whatever confidence level I have, if I can catch that. So the question that they present here is, the second part of the question is, if the EPA requires that nitrogen oxide emissions be less than 165 thousandths grams per mile, can we safely conclude that this requirement is being met, based off of this sample that we did? First of all, it was a small sample, but either way, based off of it. Well, if you look just at the mean of that sample, that mean is less. So as a best point estimate, using a single value to estimate, sample mean to estimate where the population mean would be, you'd estimate that the population mean is going to be about 153 thousandths grams per mile. And so you'd say, yeah, sure, that's less than their benchmark requirement, so the requirement's being met. But then the interval actually shows you something a little bit different here. So let's run the interval. Okay, we're going to run stats, t-distribution, one sample with the data. 1 vars, choose your confidence level. I'll make a quick remark here, but I'm not going to go into it like I did in my other video. You have some answers here that are wrong. You see the wrong answers there. 92 thousandths, 180 thousandths, and they're smaller. In other words, it would be a tighter interval than we have here. That could occur by using a smaller confidence interval, like maybe you accidentally subtracted or you didn't change the default and it said 95. It could also occur by, depending on how you're doing your hand calculations, if you would use the wrong degrees of freedom. And there's probably other ways. So I would need to know exactly first of all, which technology you used, or if you did it by hand, and then I would help you be able to look through your notes and catch your error. Okay, this time I'm not going to store it in the table. Let's just go ahead and compute it. So those are my limits, and the degree of freedom was 6. I'll show you as a reminder how to get your your critical value from your t-distribution, because that's really easy. If you have your table out, just scroll down a little bit further past the z-scores, those are the normals, to the student t-distribution. Your degree of freedom is going to be 1 less than your sample size. Okay, and then you use conventional rounding. So down here at the bottom, you'll start to get into questions that, maybe your sample size was 215. Well, 215 minus 1 is 214, but that's still 200 is the closest number I have for accuracy. I would go to 200, follow this row. And then you follow the row according to whatever column you want to match it up with. So remember, for this set, our degrees of freedom is always n minus 1. So we're looking across the row of 6 for our question. And we want area either under 1 tail or 2 tails, depending on the perspective you take. Under 1 tail, it's going to be 1%. Under 2 tails, it's going to be 2%. And here's why. If our confidence level is 98%, then you imagine the entire curve, 100% minus 98%. It leaves 2%. Now, what's that called? Do you remember? That's called alpha, right? That's your significance level. In fact, let me scroll back up here to what I'm showing you in notation, what I'm calculating. By the way, alpha, that symbol right there, let's scoot in a little bit, that's also on your symbols page. So that's 2%. So I could look under 2 tails and say, well, under all of the 2 left and right tails, 2 tails I have, there's going to be 2%, and I can go down that column. Or I can split it in half, as we're supposed to, and find out the area to the right of the critical value that we're looking for. So if I split this in half, it'd be 1% to the right in just the 1 tail. And then I'd get that critical value and multiply it by the standard deviation of my sample of 7 items divided by the square root of 7, and I'd get my maximum margin of error for all confidence intervals that I would have run. And 98 out of 100 times, I would expect that my confidence intervals would wrap around the true population mean. But there's still some chance that they won't. And that's important to remember too. So here's the 1% right tail and this 6 degrees of freedom. And that would be 3.143 times, we've got the numbers here, let's do it. So it'd be 3.143 times our sample standard deviation, which is and I want to be as accurate as I can, and that would not be. Let me skip back, I'm sorry, 0.4. Okay, and then I need to divide that by 7, which is my sample size, square root of 7. So 7 square rooted. And I get this, right? So this is my maximum margin of error. And now I'm going to subtract that from my mean. So I'll just go ahead and store this. And I'm going to add that to my mean. I'll go ahead and make it negative and add it to the mean. So that's kind of like subtracting it. I should get 103 thousandths, and I did. And then let me bring it back. So remember, I made it negative and then I added it to my mean, so that was like subtracting. Let me just directly now add it to my mean. And I should get 203, which there I am, again, matching. So those are your limits. That's the fast, easy way to do it. But what did I do? Well, what have I created? I've created a confidence interval, but it's a 98% confidence interval, and I don't want to say I'm 98% sure that, or sorry, I don't want to say, because that is true what I was starting to say. I am 98% sure or confident that this interval, this range of numbers, wraps around the true population mean mu. But I don't want to say that 98% of the time mu will fall in here, because what you need to keep in mind is mu is not moving around. The mean of the population doesn't move. It is what it is. It's the mean of the population, right? But dependent on the sample that we choose, our interval moves around, right? And how big it is and everything like that. So what we've found out is that we are 98% confident that this wraps around the population mean. But here's the problem. First of all, we're not 100% confident. Second of all, there's a lot of space on the other side of this benchmark we're supposed to be below if we're going to meet the standards, the requirement. And in fact, let me kind of draw this out. Okay, so I'll imagine this is the number line, and you know, over here is like 0, and here's this left endpoint, here's this right endpoint, and then here's the mystery population mean. We don't know where exactly it fits, but we've created this confidence interval that we are, 98% confident is wrapping around that mean somewhere in here. Maybe the mean's there, maybe the mean's there, but maybe the mean is up here. Okay, let's look at that benchmark that they gave us. The benchmark was 165 thousandths. Okay, I'm not too great at this, but I bet that right here is about a 15. So 165 might be about right here. So there's 165 thousandths that we are supposed to ensure according to the requirements from the EPA that we're below this. Well, we're not going to be able to do that. If our interval had been this tight little thing that was over here, falling completely below that, I would have felt really confident to say that, yeah, we meet these requirements. If our interval had fallen like this, and of course that would have been dependent on wherever our population, or wherever our sample standard deviation and sample mean were. If our sample mean was right here, and and depending on how big our maximum margin of error was, our interval turns out to be this wide, then I'd feel great. Yeah, definitely, this whole thing's below it. But here's the problem. Because we want to be below this whole thing and we aren't, we've got a lot of room right here to be wrong. And this wasn't even the tightest confidence level that we could have chosen. We could have chosen a 99% confidence level or 99.5 or something. So let's go back to our options. We would say, can we safely conclude that the requirement is that it's supposed to be less than 165 thousandths is being met? No. It's possible that the requirement is being met. Yeah, you can imagine from the picture here, if the population mean is right here, you can maybe assume that all of the ranges fit in there or something like that. But it's very possible that the mean is not less than that number. So that's what I'd go with. Well, the answer you went with, which is probably not where your question was. Your question was, how did we get to these endpoints? So the short of it was, I ran stat, t-statistics, one sample, and since I had the data, I just used the data, changed it to my confidence level of 98%, and I was good to go.